directly. Startup focused on deploying the first commercial space solar power platform. He graduated from Cleveland State University in '95 with a bachelor's in mechanical engineering and from the University of Michigan in '99 with a master's in systems engineering and is a licensed PE. He led advanced engineering teams at Chrysler and General Motors for 3 award-winning engine families across 8 production programs, and was the principal engineer for Raptor full flow stage combustion and Methalox rocket at Space Exploration Technologies and the director of propulsion engineering for Divergent Technologies. In developing mass manufacturing of additively manufactured technologies, he's published works on high efficiency, low operational cost internal combustion engines, carbon neutral synthetic fuel processes, and has 55 US patents. So if you would take it away, John, please.
Thank you very much for the introduction, and I will say that I am here to satisfy my professional engineer continuing education requirements because I have not published enough patents recently because they're too secret to do so. But the topic today is a little bit different than some of the other prior presentations. I'm interested in architecture level work to move the needle on performance for propulsion systems in general. Some of the prior work I'll reference today talks about that, but this is personal interest, not professional work. And the topic is a new architecture called a turbo rocket jet, which allows you to have much higher thrust to weight ratio than prior architectures. So just a little bit of background on what it is and why it's worth doing, the difference between access to orbit and other use cases, and the application for air-breathing aircraft. So this is me a long time ago when I was running this program at SpaceX. So I am an aerothermal engineer interested in a lot of topics. I do combustion professionally. So this architecture in particular is coming at it from the rocket side. I find that a lot of rocket development engineers and gas turbine engineers don't talk to each other and understand what the trade-offs are. So I'm maybe uniquely positioned to understand both and apply the capabilities of both kinds of technologies for a use case in this case. So turbo rockets are a type of propulsion system that, in this case, you're leveraging air-breathing portions for the launch mission such that you can reduce propellant mass. Normally, rockets are like 95% propellant, so the payload you can carry is relatively low compared to the size of the vehicle. So a turbo rocket leverages that with a single flow path device that both combusts air and combusts storable propellants on board using cryogenic propellants. A turbo rocket jet is basically the same thing, but you're also doing air breathing, but you're using storable propellants because you don't want to have the cryogenic infrastructure for the airports that you're operating out of. So just in general, you guys probably all know this, but you're extracting enthalpy from a gas generator, in most cases through a power turbine, and the atmospheric oxygen and storable fuel are your two propellants you're going to use, and frankly, air is great because you're like 70% diluent, so your peak temperatures are relatively low compared to rocket combustors. Same thing on turbo rockets. You can extract enthalpy from combusting propellants. I've done one with a fission reactor, and you can get the shaft power out either through a power turbine, or in the case of some of these devices, you can put the rocket nozzle on the tip of your fan and extract shaft power that way. And cryogenics are just the highest performance rocket, and you need it for the rocket portion anyway. And so these systems all operate really fuel rich, like equivalent ratios of 5 through the power turbine, and then that is injected into the airstream and combusted so that you get jet thrust. The turbo rocket jets are very similar, except for you have 2 parallel gas generator paths, one through a rocket combustor and one through a conventional. And in this case, again, storable propellants such that you can not have to have extra infrastructure at your endpoints. Same thing, you're running the rocket combustor really rich, such that the nozzle discharge into the airstream is able to produce jet thrust. So this chart maps the major performance metrics of the types of propulsion systems you might want to use. How we have thrust on the y-axis and thrust to weight on the x. you can see that you can have really high thrust to weight, relatively speaking, with afterburning turbojets, but turbofans are much better for efficiency, number one, but they're more massive for the amount of thrust you get. Rockets are way on the right, and you can get 200 to 1 thrust to weight ratios, and the two on that axis are both things that I've touched. Turbo rockets are somewhere in the middle. So getting more thrust is relatively easy. You just scale, run more mass through your system, and run it that way, more velocity. But going to the right, thrust to weight is challenging because you got to have more and more pressure ratio and more temperature on your the outcoming stream to get that thrust ratio up, and that's why rockets do so much better, because they're running hotter at much higher pressure ratios. So one of the things that I'm introducing in this area is a topic that a lot of combustion engineers don't necessarily understand, but ignition delay, the process by which a liquid fuel transitions into combusting, is heavily temperature related. This chart shows mixture temperature temperature over the mixture temperature on the x-axis, and ignition delay on a logarithmic scale on the y. And so all the propellants or fuels of interest, as you get them hotter, their ignition delays drop off exponentially. And that's one of the reasons why a lot of air-breathing combustors using cryogenic propellants struggle, is because it takes so long from the cryogenic propellant just to warm up to combustion temperature that you end up having the propellant can be far downstream. It doesn't ignite, and that's why you have bluff bodies and other devices in your combustor to allow those systems to recirculate long enough to warm up and have the ignition delay occur. But if you were able to operate in a regime where your combustor temperature, your propellant temperatures are very, very warm, you can get ignition delays almost effectively zero. And that's actually what physically happens, is that your ignition delay goes to zero once it's warmed up in a combustor, and then ignition occurs because you have that chemical reaction. So your fuel temperature can do the same thing. So in the use case for the access to orbit mission, the turbo rocket itself goes through multi-modes, even though it's all one device, where you're getting mostly jet thrust, and then you're converting to a ramjet, so you're not capturing as much of the energy from the jet, the rotor itself, and then eventually the velocity through the combustor is supersonic, and then you do a pull-up maneuver and run rocket only. And it's interesting that even in this use case, the vast majority of the propellant is used in the rocket portion, but you need that because there's no atmospheric oxygen to look at. And if you look at this chart, free stream Mach numbers on the X, and specific impulse, which is just pounds per second of mass flow of the propellants versus thrust, even just improving the average a little bit over the rocket thrust, which is this Mach 15 and higher, you can get 10x more payload, because you're doing, number one, the thrust is a lot higher during the air breathing section, and you're burning much less propellant for that thrust, and that's the portion where rockets spend most of the time, most of their mass on ascent. So if you want to know more, I published 2 prior papers on this, once in 2015 and once in 2018. And you can see that I've just recycled this presentation from 2018 as well, at least the theme. So back on the topic of turbo rocket jets, I'm actually designing for a couple of missions of interest to me. One is a vertical takeoff. The challenge with vertical takeoff is your thrust weight on your propulsor, basically. And there's been lots of attempts. You might have seen this chart before, but there's only basically 4 operational solutions for vertical takeoff. You have helicopters, which are relatively straightforward, and all the others, which have big drawbacks compared to a fixed mission. And again, if you were to install more and more propulsor mass to get the thrust up, you end up with less and less payload. The other big one is having takeoff performance for just a fixed-wing aircraft, not necessarily vertical takeoff, and getting the design point to be somewhere in the middle of the rating range as opposed to the maximum. So turbofans generally have amazing thrust at takeoff, but their fuel consumption isn't great, and then their thrust drops way, way off at their design condition at cruise. So what I'm going to talk about is, I have this architecture that I'm interested in. So normally what you do is you pick a notional example and you run through all the analysis to figure out how it's going to perform. I've picked a relatively small 500 millimeter diameter compressor fan reference. It's the Williams FJ33. It's used in small biz jets and also some other personal jets. It's relatively relatively new. It's less than 25 years old. It's about thrust to weight ratio just under 6 and has a 3.5 to 1 bypass ratio. I've used something similar in sizing just for comparison's sakes, using Jet A as the fuel and high test peroxide, which is the peroxide is H2O2. It decomposes to hydrogen and steam in the presence of a catalyst, and it's mixed with a little bit of water for stability. And very similar pressure ratios, but at least on the bypass side, but the cores run at higher pressure ratios just because there are newer things available. And it's dry thrust. You can see it's about double just because of those improvements. But really the augmenter is the big deal. So you can see that you go from 8 kilonewtons to almost 53. And a bit smaller dry mass, and I'll talk about why that is a little bit later. But you can also see the specific impulse, which is the same as ISP, is substantially lower just because of the pressure ratio. And thrust to weight, at least in the missions of interest, much, much higher, as you can see. So here's a drawing done with NASA's VSP, just because CAD's challenging sometimes to draw things like this, just to give you guys a feel of the architecture. So I'm actually using a tandem rotor on the thrust fan. I'll talk about that in a minute. So relatively high bypass ratio. The core's got one 8-to-1 compressor stage, and then it's got 3 high pressure turbines and then another 5 low pressure turbines with the rocket combustor hiding out in the small area. The 3 stages extract shaft power, which drives the low pressure shaft that runs the compressor, and then the rocket exhaust exits through the stators and out these nozzles, and then you have a mixing zone and a variable nozzle. So tandem compressors are great. You can get much higher pressure ratios of over 2 with acceptable efficiencies, and you can look at this up on the paper, but effectively what you have is another booster rotor in front of the main rotor. Allows these pressure ratios to be achieved, which is great for a turbofan. Also, if you're interested in cylindrical compressor design, this is a 3-way splitter solution. Allows you to get almost 10-to-1 pressure ratio of interest, but only using 8 in this use case, and that allows me to eliminate 3 axial compressor stages to get the same overall pressure ratio, and it's just a mass savings and a volume savings. So I'm giving the end result first. Here's a chart of about 6 different states that I've done the analysis on of the performance with the reference jet on the left. And you can see that there's 3 unaugmented points and then 3 augmented points. And you can see that the fuel flow rate, propellant flow rate goes way, way up, and augmentation just like you would do in a normal afterburner, but you can see that the amount of augmentation is dramatically higher than conventional turbojets. So just to give you an idea how the system operates, this chart shows right to left, relatively low idle speed operation. You can see that most of the thrust is coming from the thrust fan. I don't know why there it is. It's not showing on this screen. Okay, well, I'm pointing, but at low power, your turbofan up to a point, you add augmenter, you get a lot more thrust from the increased temperature specifically on the thrust fan output, and you can see that the rocket actually is not generating a lot of thrust at all. It's all the augmenter because you're extracting the shaft power to run the compressor at higher power levels. So overall, these systems are being constrained about 1300 Kelvin, 1000 degrees C, just so they can run uncooled, low-cost parts. You can see that all the systems are constrained to relative to that, and the core fee is only running about a quarter of stoichiometric. A lot of afterburners run substantially hotter. You can run all the way to 1 on a conventional afterburner if you have the ability to cool the walls. So this system could potentially have higher performance if we were to go down that path. And then this chart also shows where the shaft power to run the thrust fan is coming from. The system obviously has, it's supercharging the core stage a little bit, so you have more pressure ratio. So the system runs up to just under 2.2 pressure ratio, and you can see that the substantial amount of the shaft power shows up at the higher augmented ratios. So this system, this architecture solves a lot of design mission challenges with 10 times higher thrust to weight. So you can either have higher payload for power lift solutions, reduced dry mass for improved takeoff with fixed wing. I did a quick analysis for a turbofan vehicle, the Cirrus Vision Jet. It normally has a 600 meter takeoff run. You can do it in under 100 meters with basically the same size and same mass installation, and it can get to altitude in under a minute as opposed to the 10 or 15 it takes. And again, getting augmentation up to that levels it offers some opportunities for some mission designs. And right at the end of this design process, I found Rolls-Royce had something similar in concept-wise. So I would just want to say this, I'm not the first to come up with this, but at least there's a paper you can read. Rolls-Royce did never publish anything on this topic. So thank you for your attention, and happy to take any questions.
Okay, we opened it up we have about 3 or 4 minutes for questions. So if you could raise your hand and then please state your name and affiliation if you will. Yes,
Dave Brown, Spectre Aerospace. I was curious, you mentioned a RAM and a scram phase, but the kind of CAD model that you showed didn't seem to have any kind of...
That's because that's the turbo rocket. That's the 2 prior papers I published on the ascent for the mission design, because those were originally designed for access to orbit missions. This is for like sub Mach conventional propulsion. I mean, you could add an inlet and go higher Mach, but yeah, this is not access to orbit mission design. Happy to talk about that though. That's fun topic.
Logan Freeman, Utah State. From a materials perspective, are there, that obviously is going to be a higher exhaust temperature. Is that beyond what current, like after burning turbofan jets run?
So this 1300 Kelvin design point is designed around Inconel. Inconels can run with enough structural margin for most use cases right around 1,000 C, between 950 and 1,000. If you go into the cooled regime, you can get over 2,000 Kelvin easily. So yeah, there are solutions that are just generally more expensive. But a lot of conventional systems, I think GE's combustors that use their first stage turbines with ceramics are right around there, 2,200 Kelvin, I think, is where they're operating today. I saw one more over here.
Yeah, I think there's somebody put their hand up.
I was just curious about the airport operations with peroxide.
Yeah.
I'm not sure what percent that is, but
You can vary. This one's 80%. You can go as high as 98.
pretty exciting stuff.
Yeah, I mean, so I would argue that operationalizing peroxide is possible. The biggest thing you have to worry about are manageable. I mean, there are things you're already dealing with today that are. It's non-toxic, which is great. But yeah, operationalizing it means you have to worry about the materials of the interfaces and things like that. But yes, I mean, no one's doing it today because there's been no need, frankly.
Okay, well let's thank the author one more time.
Yeah, thank you.
Get our next